Good morning, everyone. Welcome to the security track down here. Today we will hear a lot about different platforms, different architectures, starting with ARM and Sandrine. Give a big round of applause for her. She will be speaking about secure partitions.
Thank you. Hi, everyone. So thank you for joining me today. So I'm Sandrine Bailleux. I work at ARM, more specifically in the Trusted Firmware A team. And today I would like to talk about secure partitions. But before I do that, I'd like to give you a brief overview of what the project is. So the aim of the project is really to provide a reference implementation of a firmware for the ARM v8-A platforms. Yeah. So as I was saying, the Trusted Firmware A project is about providing reference code for the firmware on ARM v8 platforms. So on the right, you've got a picture of how a typical software stack might look like on an ARM v8-A platforms. So this is showing a device that would have the trust zone technology, where the world is divided into two parts. You've got the normal world that, on the left, which is running all your normal applications, your operating system like Linux, and potentially your hypervisor. And on the other side, you have the trusted world, where you run all your secure payloads. So you might have some trusted applications running on top of a trusted OS. And at the very bottom, we have Trusted Firmware A, which is running at EL3. That's the the highest level of privileged on an ARM v8 platform. And so the aim is really to provide a foundation for people to build such a trusted execution environment. The project, the code is designed as much as possible to be reused and to be easily ported to new platforms. It's an open source project, otherwise it wouldn't be there. It's available on GitHub and distributed under BSD3 closed license. And the project was created about 5 years ago. I believe it's the anniversary is this month. And so over the years, it's got some traction from partners. We've got about 30 platform ports available today in the upstream. So I wanted to list some of the main features of the Trusted Firmware A. So obviously, being the first piece of software that runs on your platform in the trusted world, it has to boot everything and to initialize your secure devices. It's got a modular boot flow where the firmware is divided into several images: a ROM firmware, RAM firmware, a persistent RAM firmware that provides some runtime services. So you don't have to use all of these images. You can pick some of them only and potentially replace others by your own implementation if you have different needs. It supports trusted boot, where every firmware image authenticates the next one before executing it. So you build a chain of trust from the very first piece of firmware. Also, it's since we have this concept of normal world and secure world, sometimes you've got to do some transition between the two. So that's the trusted firmware handling this world switch. You can integrate the trusted firmware with a trusted OS. We support a number of popular ones. This is done by implementing a piece of code in the firmware to basically intercept all the requests that are targeted to this trusted OS and forward them to the trusted OS. It supports a recovery mode in case your device is bricked and you need to update the firmware. And also, much like UEFI, it provides some runtime services. So it stays in memory at runtime once your OS is booted. And the OS can make some calls into the firmware. One of these services is, for example, power management. So I said that the code is available on GitHub. I wanted to take this opportunity to introduce trustedfirmware.org, which in a couple of months will be the place where the code will be available. just about where the code is available. It's a kind of a new era for us because the project will become soon a Linaro community project that will host both the trusted firmware A, but also its counterpart for M-class devices, the trusted firmware M. The M-class devices are microcontroller space. This project will be operated independently from the main Linaro organization. There will be a board of members, so anyone really can join the board, and whether they are a Linaro member or not. And the benefit to being a member is that you'll be able to piggyback on the infrastructure provided by Linaro, for example, to get your board integrated into their board farm so that it's so that the firmware is continuously tested against regression, and potentially also influence the direction of the project for the new features and everything. So if you want to know more about that, please go to trustedfirmware.org or contact board@trustedfirmware.org. So now let's delve into the heart of the subject. What I want to talk about is very much related to the challenges that people face today into the trusted world. Before I start, just as a disclaimer, this is kind of a hot topic. It's something we are currently working on, that we've been working on for some time. So it's still, nothing is set in stone yet. Things might evolve, both on the specification side of it and also on the implementation side of it. But hopefully I can give you an overview of the concepts and why we're doing that and how we are going to do it. So one of the challenges that people face today in the trusted world stack is that the ARMv8 architecture, I mentioned Trust Zone that provides you the separation between normal world and trusted world. And the concept is really that the software running in normal world cannot interfere with the software in trusted world. So it cannot, for example, it cannot access secure memory, secure devices. So there is a nice separation there. But beyond that, we don't really get any isolation. In particular, so here on this diagram, we see the trusted firmware A running at the highest privileged in EL3. And the trusted OS is typically running at secure EL1. And there is no proper isolation between EL3 and secure EL1, between the firmware and between the trusted OS. So that means that EL3 and secure EL1 both have basically the same level of access to the memory space. They can access any memory they want, and they also get direct access to the physical interrupts. So as a consequence, you have these orange arrows that I've drawn is the interactions that can happen. So the firmware in EL3 is never really isolated from the trusted OS. If you've got several components inside your firmware, they are not isolated from each other. And also the normal world cannot be protected from the trusted OS in secure EL1. And there have been some attacks in the past where people would leverage some bug in some trusted OS implementation in order to access the normal world and do some privilege escalation attacks. So that is a real problem. The second challenge that the software stack is very much fragmented. So here we have a picture again of the same software stack. I've just put some colors to identify who provides the code and the dependencies. So let's start first with the green boxes. So these are all the trusted OS specific things. So unfortunately, when you have a particular platform, that some dependencies on other software components. Although there are some standardization at the application level to communicate with the operating system, the standardization doesn't go beyond that. So if you've got a particular trusted OS, you've got to have the corresponding trusted OS driver in your operating system and potentially in your hypervisor as well if you have one, in order to be able to communicate with this trusted OS. And the same goes also in the ER3 firmware. You've got to have some kind of dispatcher that will basically intercept all the requests for this particular trusted OS and forward them in a trusted OS specific manner to secure EL1. So yeah. The other thing is that the code is coming from different vendors. So obviously there's the trusted OS vendor, like I just explained, but potentially there is also some code provided by the silicon vendor. If you need to access to some particular trusted hardware resources, you most probably will need some driver into the EL3 firmware and into the trusted OS. And the fact that there is no proper isolation between the trusted OS and the firmware, and that it's provided by different vendors, means that these people have to trust each other. These software images has to cooperate to some degree, and that's an issue. So the solution that ARM proposes is to introduce virtualization in the trusted world. So maybe you've heard that there's a new version of the architecture coming, ARM v8.4, and that will give us secure virtualization extensions with a new exception level, which is secure EL2. And that will allow us to run some firmware code at this exception level. And it will be very similar to the counterpart, I mean, the EL2 in the normal world where people run a hypervisor at the moment. So that means that the hypervisor will, the secure EL2 firmware will be able to restrain access to the physical memory for the trusted OSs, because trusted OSs will no longer access directly to physical memory. Instead, they will access to intermediate physical addresses that are then translated by a second stage of the MMU by the secure EL2 firmware. So you've got two stages like that, and so the secure EL2 firmware can control like that exactly what physical memory is accessed by the trusted OS. And same for the physical interrupts. They will be routed to secure EL2 instead of the secure EL1. So that means that the secure EL2 firmware controls them. And if it deems that it's an interrupt that it needs to forward to the trusted OS, it can re-inject it as a virtual interrupt into the trusted OS. So these are all the hardware features that we'll get with ARM v8.4, but of course we also need a software architecture to leverage all of this. And that's where the secure partitions would play a role. So a secure partition in this context is a software sandbox that runs in trusted world. So it's a sandbox. That means that it's isolated from other secure partitions in the system and from all other software entities. And it runs at the low privilege exception level under the control of higher privilege software. And the aim is really for a secure partition to provide secure services. So just to illustrate, give you a bit better idea of what a secure service is, you may think about platform-specific services. Think about RAS error handling, so that when you've got a hardware error, like a memory corruption, something, it might be fatal. You might not be able to recover from this error, but you might at least be able to read some platform-specific register that will give you a bit more information about how this error occurred, in what circumstances, and build an error report. So that's something you could do. You could implement in a secure service. You could also have device-specific services. If you've got some cryptographic hardware on your platform, you might want to have a dedicated secure service that controls this cryptographic hardware, and all the rest of the software stack would have to interface with this secure service to access the cryptographic hardware behind it. So these are two examples of quite hardware-related secure services, but you can also have some higher-level services to implement protocols like secure storage, secure payment, or secure firmware updates. And all of these secure services and secure partitions are meant to be independent of any operating system, because remember, one of the challenges in the trusted world is really that we have this dependency on the trusted OS. So by standardizing the communication interfaces between the secure partition and the rest of the world, we would remove this dependency. Now, so this is how the world would look like with secure partitions. So in the green boxes, you've got two examples of secure partitions. So the first one is, let's say it's a simple one that would run both in secure EL0 and secure EL1. But you can also have more complex secure partition that encapsulate a whole trusted OS and its trusted applications. So, and you may have as many secure partitions as you want in your system. So obviously you need some kind of entity that manages all of them. So that's the, in the yellow box, the secure partition manager. So that's the bit of code that would run at secure EL2. And conceptually, it's very similar to a hypervisor that would manage its guest operating systems. And the secure partition manager is provided by the Trusted Firmware A project. The project will also continue to ship the ER3 firmware as well, obviously. Now, so unfortunately, ARMv8.4 is not there yet. So for the time being, we don't have any secure EL2, we don't have any secure virtualization. So that's how the software stack currently looks like. So since there is no secure EL2, the secure partition manager currently runs at EL3. And it's part of really the same binary as the rest of the Trusted Firmware A. And the secure partition run at secure EL0 because, as I said, there is no proper isolation between EL3 and secure EL1, so we don't want to put secure partition at secure EL1, otherwise that kind of defeats the purpose of secure partitions. And we just have a bit of glue code, this other yellow box. It's just because architecturally it's not possible for secure EL0 code to call directly into EL3 code. The way you do that usually is by executing an SMC instruction, secure monitor call. That's an undefined instruction for secure EL0. So we've just got a bit of glue code that relay SVCs that, secure EL0 code can make a supervisor call into secure EL1. So we just have a bit of glue code that we relay SVCs into SMCs. And that software architecture enables us to start implementing SPM with the current architecture. Now, I just wanted to give a bit more detail about some of the implementation details of secure partition, mostly around their runtime model. So obviously, a secure partition provides some secure services. So we need a way for the other pieces of software to request these services. So we need some kind of communication model. So we've implemented a client-server model where in this context, the server is a secure service. And the client can be either running in the normal world, so it could be your bootloader or your operating system. But it can also be another secure service in case you have some dependencies between secure partition. Earlier, I was talking about a secure service that would drive your cryptographic hardware. In this case, that will probably, that might involve a dependency on another secure partition that would like to implement secure storage, for example. So in terms of implementation, a secure service is really just a passive bit of code that waits for something to do. So it's just a loop that waits for some input, and when it receives some work to do, it just processes it and then that's forever. And for every communication between a client and a secure partition, everything goes through the secure partition manager. And one important thing also is that we want as much as possible that the normal world software stays in charge of scheduling. What I mean by that is that we don't want the secure service to execute for a very long period of time, because that would result in a blackout from the point of view of your Linux kernel, for example. So if you've got your scheduler in Linux that is trying to take the best decisions, on what application to schedule, having the secure world stealing all having the trusted world stealing all the CPU cycles like that would mess up everything. So it's really if the normal world thinks that some service is taking too long to complete, it can always interrupt it. That might not be the case in all. It's not the only model that we will support, but that we see that as the main one. So, as I said at the beginning, one of the issues in the trusted world is really that we don't have any standard. One of our aims is to standardize all these communication interfaces. So ARM is introducing two new specifications, one for the clients to request some services. So that's the Secure Partition Client Interface, or SPCI. And another standard is for secure partitions to actually handle the requests that they receive from clients. So that would be standardized by the Secure Partition Runtime, or SPRT. These specifications are still under development at the moment. And the aim is for the Trusted Firmware project to provide a reference implementation of these standards. And this is still under development as well. So the SPCI is really just a collection of ABIs for clients to discover the secure services that are available on your platform. Each service basically has a unique ID, so the clients, that's how they refer to a secure service. The Secure Partition Manager basically keeps a kind of a registry or a database of all the secure partition IDs in the system, and by which partition this is implemented, so that it can forward the request to the right partition. The SPCI also obviously allow clients to establish a communication channel with a given secure service when it's been identified, and exchange messages with this secure service. And if there is kind of a big payload to attach to this request, there is a possibility to share some memory between the client and the secure partition to put the payload inside. And on the other hand, the SPRT is again a collection of ABIs but this time provided to secure partitions. That's implemented by the SPM again, and it allows secure partitions to retrieve client requests, to send responses back to them, and to receive any interrupts that would be targeted to this secure partition. Either some interrupts potentially might have a secure service that handles a device, so it would own all the interrupts of this device, or it can also be some inter-process communication between the secure partitions if they want to send interrupts to each other. And the SPRT, this runtime model, is really there to provide a frame for people to implement secure services on top. So it eases the development of secure services, and it also improves the robustness and the security of secure services, since people don't have to reinvent the wheel from the beginning every time. So remove some of the usual mistakes that they could make in the implementation. So hopefully this gives you an idea of why we are working on that, and what we are trying to achieve, and how we're going to implement that. I've put a few links to have a look at your leisure, mainly to the Trusted Firmware A code. And also, the last link is a white paper from ARM that basically talks about what I just presented in more details. So if you want to know more, I invite you to have a look at this one. Do you have any questions? Okay.
Hi. So my main question about this architecture extension with the secure EL2 is essentially why don't you just have the secure server, because there's already a separation between secure EL0 and EL1, right? So why can't you just only have the secure services in EL0 and have a common implementation of secure EL1 that could be part of Trusted Firmware or could be another ARM project, and then have your common ABI between EL0 and EL1, and then you wouldn't, like right now you essentially have 2 layers of isolation where I think you only want 1, right?
Right, yeah. So the main issue is that, yeah, I should have said it. So people want, at the moment, so I should go back to one of the diagrams just to illustrate that. So at the moment, oops, let's take this one, yeah. Most of the time, people only put one trusted OS into their software stack, because it is possible to have multiple trusted OSs, but it's kind of difficult. They have to cooperate with each other. And so if we were to implement it the way you said, basically, so we would need to have if you have 2 trusted OSs, you would need to have one of them that implement the standard for the rest. And so it wouldn't be very scalable because it will again introduce this problem of standardization. So yeah, the aim is really to have a more scalable software stack in the trusted world, where you can have multiple trusted OSs sitting alongside secure partition that do not have anything to do with trusted OSs. So that's why you have to kind of have something at a higher exception privilege that manages everyone, basically.
But sorry, so right now, is there anything you actually gain from having more than one trusted OS? Because couldn't you just have one trusted OS that's maybe developed from ARM that all vendors could use?
So ARM don't develop any trusted OS, and we will not. But yeah, I mean, people want to be able to have several trusted OSs on the same platforms. I mean, they've said it to us. It's mainly for OEMs when they integrate all the software on their stack. They may be interested in having several trusted OSs.
Okay, thanks.
Yeah.
Hi, thanks for the talk. I have 2 questions. Like, first is, can you tell what are the top business cases for having multiple trusted OSs, or top cases for trustlets? And last year, Google Zero Project announced problems with revocation of trustlets. Can you let us know what would be the procedure for revocation in new cases, and how it works from our perspective?
Right. So for the first part of the question about having multiple trusted OSs, to be honest, I don't know because I would imagine that different trusted OSs provide different services, but I've never really looked at what kind of services. I know that trusted OSs are mainly used on mobile devices. It's not so much targeted towards the server market, for example. So yeah. So trustless. So do you mean trusted application running on right? So about revocating these, like you mean if one of them is has a vulnerability inside it. Right, but in this case, as long as you don't have any vulnerability in your trusted OS, if you've got one in the trusted application, that shouldn't do much damage, right? I mean, if they because the trusted OS controls all the resources that every application can access. So I'm not too sure about the.
Okay, you assume that trusted OS would be not vulnerable, but if it would be vulnerable, what's then?
Yeah. Okay. So if the trusted OS is vulnerable, yeah, that's another issue. So with SecureEL2, again, we would have a higher privilege exception level that can control that. But again, you can have a bug in SecureEL2, but then you can make a case of that for every piece of software, I guess. And
yeah, but in case of your virtualization layer, I believe we should not care much about that, but more problem we probably will have with trusted OSs and trustless, because those are deployed by multiple vendors, which may not care to harden that so much as you hardening your firmware layer, which have to cooperate with various trusted OSs. So still the question is open, like how we revoke applications which are inside phone and in the field, like we have like millions of phones there, and what's that?
So I think it's more of this is an issue, I would say, that the trusted OS itself would have to handle in any case. It's really implementation specific, I guess. I'm just giving you my, I mean, I don't know for sure, okay? I'm just extrapolating. I think that if you want to be able to revoke your applications, you need to implement some kind of signature in your application, and perhaps having a registry in your trusted OS of what application you trust and which one you don't, and you can always revoke applications there. But I don't think it's something that concerns SecureEL2 or EL3 firmware. I think it would be handled at higher stacks.
Yeah, I think that one of the problems is that for example, some main vendors of trusted OSs just don't have the path for that. So that's the case, and that's what Google Zero project pointed, like July 2017.
Okay. Yeah.
But the trust OS is part of the static firmware, so you just replace it.
Yes, you can replace it. Yeah, absolutely. I mean, it's loaded anyway by the firmware. So yeah, you can always have to have the firmware enter some recovery mode where it would update the trusted OS on secure storage. Yeah.
Yeah, so I have another question. So holding the mic, so I'll just... So you were talking about scheduling blackouts before. Yeah. Can you explain, maybe, if it doesn't take up too much time, how that works actually? For instance, if you do call into a secure partition from a guest OS on the non-secure side, and its time slice runs out, how does that get scheduled out and back in again? Because it's kind of inverted from the normal scheduling case.
So the idea is is that secure partitions are interruptible by normal world interrupts. So you can have your operating system programming some kind of timer interrupts, which makes sure that it fires every fixed amount of time. So if a secure service is taking too long to run, it would just get interrupted by the timer, and that would I mean, the interrupt would be targeted to your operating system, which would then choose or not to choose resuming the request of the secure service, or if it doesn't want to, then it doesn't have to.
So it schedules. So the hypervisor reschedules it. Does that mean that the call from the secure partition has to return first, then it gets rescheduled, and then the call is like restarted, or?
Well, Your secure service would be running, okay? And at this time, you've got a timer interrupt that fires. Automatically, because we've configured the right routing model inside the general interrupt controller, the GIC, this interrupt would automatically stop execution of the secure service. And then, because the interrupt is targeted towards the operating system, that's where it would be delivered, and you would basically enter your vector interrupt inside your operating system. So then the operating system can figure out that it had made a request to a secure service, and it can figure out that it has been interrupted, and so it is free then to resume this request later on, or do some urgent work first and do it much later. Does that answer your question?
Yeah, so you don't actually context switch the state inside the secure partition. So you don't have re-entrant calls into the secure partition.
No, we don't have any re-entrancy, but we would still, I mean, yeah, there's a step that I forgot. Yeah, you're right. You've got to at least save the state of the secure partition, enable to resume it. That would be done by the ER3 firmware just before forwarding the interrupt to the normal world. Yeah, sorry.
Hi, nice
Hi.
talk. If I understood you correctly, that requires new hardware features.
Mm-hmm.
In what core will they be available?
So it will be in the core ARM v8 architecture, so all cores. But the only thing I'm not sure about is whether these hardware extensions will be optional or not. They probably will. In the ARM v8 architecture, so we often have new revisions, and every time they introduce new features, and some of them are mandatory to implement. So if you want to have a v8.4 architecture, then that means you implement these features, and that gives some guarantee to the software that they are here. And some of them are optional. So ARM provides some guidance about how to implement them, but people don't have to actually implement them to claim that they are v8.4. So I'm not entirely sure whether the secure extensions are mandatory or optional, but in any case, that would concern any ARM v8 core, so all the Cortex-A that are ARM v8.4 compliant.
Current Cortex-A72 is not 8.4,
No, it's not.
8. Whatever.
Yeah.
So when will we have an 8.4
Okay.
capable core from ARM?
Okay, so the extensions, I mean the ARM v8.4 specification, so I mean the document published by ARM, that should be available sometime around October. But then ARM doesn't implement any ARM v8.4 cores itself. Some people might in the future, but I don't know exactly.
On your pre-v8.4 design about secure partition manager, which is running secure EL1, where does your trusted OS is running to?
So let me just go back to this. Yeah,
on this one. So where does your trusted OS is sitting?
Right, yeah. So in this model, you can't really have any trusted OS. That's the thing.
Our recommendation is to not have any trusted OS on the current Cortex-A.
Well, if you want, you cannot have in the current architecture. Sorry, you cannot have partitions running at secure ER0 alongside with some trusted OS because you don't have the isolation, like I said, between secure ER1 and ER3. So that's, I mean, it's possible, but then you don't have it's kind of a fake, right? Because it cannot defeat the purpose. So yeah, that's why there is no trusted OS there. Yeah, but with v8.4, obviously, all of that becomes possible.
And quick question about trustedfirmware.org. You mentioned the code we moved to the website. Does it mean it will not be on GitHub anymore?
So I believe the plan is really, that it won't be available on GitHub anymore. At the moment, we've got the main code on GitHub, and we've already got a mirror of that on trustedfirmware.org. So you can already go there, and there's the code, both for the Trusted Firmware A and the Trusted Firmware M. But in the coming month, the plan is really to move everything there, the review, the code, everything, having our build infrastructure more open as well.
But to be as open source as now?
Yeah.
Okay.
Finish. As we just discussed, ARMv8.4 is quite some time to go. We are currently at ARMv8.2. There are implementations out. You started out at the first slide of your old slide deck, also including ARMv7. Is Trusted Firmware A only about ARMv8, or is there a version, or can I somehow compile it for ARMv7?
It also supports ARMv7 platform. Yeah, it does. I mainly talked about ARMv8 platforms because that is our main focus. But there was some traction from people to have it for ARMv7 as well. So yeah, it is. Yeah.
7 or 32-bit V8?
Both. Yeah.
All right, so thanks, Sandrine.
Thank you.